Hi everyone, I'm here with a little mini lecture for 8.10. We're going to start doing some vertical transformations on sine and cosine graphs. First, I want you to think about how we do any transformations to any function, where we've got the general rule of some function f of x can be transformed by multiplying by a. The entire function is multiplied by a. The x variable can have a value subtracted from it, and the whole function can have a k added to it. An example of that with x squared, to remember what this looks like for a parabola, that the basic function x squared can be transformed so that we can multiply by a, subtract h from x, and add k, and that in both of these cases we have the effect of shifting vertically. Tell me if you guys find that circle distracting or helpful. We can stretch vertically. And here what we're doing is shifting horizontally, because we're affecting just the input variable, not the output variable. Inputs happen on a horizontal axis, outputs happen on a vertical axis. There is also a way to stretch horizontally. We are going to see that in this unit. It wasn't relevant when we were talking about parabolas, because that is something that can be simplified out of that parenthetical piece of the function and can be kind of combined with a, so to speak. And basically, because if you think about like taking a parabola, squishing it in from the sides has the same effect as stretching it vertically. So we never had to deal with a horizontal stretch before, but we will encounter that in this unit. What we're now going to start doing is applying these transformation rules to sine and cosine. So now you can see we have the sine function, the exact same things apply. We can multiply by a value to stretch vertically. We can add a value to shift vertically. Inside the variable, we can add or subtract a variable, or a value, in order to shift horizontally. And what we are going to encounter in the next little mini lecture is that we're going to actually get a little b in there as well for a horizontal compression, and we're going to get to that in the next lecture. All right. Before we look at an actual graph, I just kind of want to remember what the overall effect is when we multiply versus add. So when we add, we are going to take -5 plus 3, -1 plus 3 shifts it into a positive, 0 plus 3, and 3 plus 3. You can see what has happened is that all of these values have increased by 3. This has moved up 3, this is up 3, this is up 3, this is up 3. They've all increased equally. When we multiply, that effect is somewhat different. Now, this isn't increased, this is now decreased, and it's decreased in quite a large way. -1 is going to decrease, but not as much. 0 times 3 isn't going to change at all. 3 times 3 is going to increase. So now we have both decreasing and increasing happening, as well as no change at all when we multiply by 0. What we've done is change the distance between those minimum and maximum values. We've increased the minimum to the maximum. Visually, what this looks like is right here. So we've got in the middle, we can see the effect of adding. Literally add 3, add 3, add 3, and add 3. Visually shift everything upwards 3 units, and the function maintains the same shape. On the far right hand side, you can see what happens when we multiply. That -5 became 3 times bigger. It has stretched 3 times farther away from the x-axis. Likewise here, and notice how 0 has remained the same. Right? It is already on top of the x-axis. Multiplying that distance by 3 means we still maintain distance from the x-axis as 0. So we are stretching away from rather than shifting upwards. This is the effect of multiplying. This is the effect of adding. So let's look at how this affects sine and cosine. When I'm going to look at the sine graph and I want to shift it upwards, I am going to literally shift each point exactly the same amount. I want you to think for a moment about what this resulting function is that I've just graphed, or that I'm about to graph rather. So it's not going to be quite as smooth because I don't have all those intermediary points. I'm using my minimums and maximums to help me. All right, so thinking about it, what we have here is the function sine of x, but I am literally shifting it up 1 unit. This is y equals sine of x plus 1. I could do the same thing. I could subtract 2. This is going to be kind of off the graph a little bit. I don't have enough space for that. Again, subtract 2. Didn't give myself quite enough room. But here now we have y equals sine of x minus 2. Okay? Let's take a look at multiplying. Now, let's think about y equals sine of x. Oops, I didn't give myself enough room in there. I meant to say y equals 2 times the sine of x. So now again, I'm going to increase that distance from the x-axis by that a factor, that a coefficient of 2. So a equals 2 is also telling me, by the way, that my amplitude of the function is going to become 2. My original function has an amplitude of 1, but I'm going to multiply that distance times 2. The zeros are going to stay the same, but my maximums are going to double. My minimums are also going to double. So my minimums also become lower. The effect is a vertical stretch. Try to get this connected for you. There we go. And you can see that it is vertically stretched farther away from the axis. Notice how my amplitude is now 2, means how far away the wave is oscillating from that midline of 0, of y equals 0. My minimums and maximums are now -2 to 2. That is my range. All right. What if I multiply by a negative? Let's take a look at y equals -2 sine of x. 0 times -2 doesn't matter, stays 0. But 1 times -2 becomes -2. I do stretch the distance away from the x-axis, but I'm also multiplying by that negative and creating a reflection. -1 right here times -2 becomes a +2. So I am both stretching by 2, but I'm also reflecting because of that negative. So the end result looks something like this. Sorry, gotta kind of turn, sorry, I'm trying to turn my iPad the right direction and I'm making it more difficult. Oh, come on, where's my pen? There we go. All right, so it's a little too pointy, but that's basically the idea. So it is stretched, it does have an amplitude of 2, but it's also reflected. Same thing is going to happen if we do times -5. It's going to be stretched, but it's going to be 5 times taller with an amplitude of 5. Okay, now let's take a look at how we can combine these effects. We can put the addition and the multiplication together. I also want to use this as an opportunity to demonstrate a fractional a value for you. So let's consider the function y equals sine of x times 1/2 minus 3. Here I'm going to both have that vertical shift in the -3, and I'm also going to have that vertical stretch, but it's a stretch by 1/2, so I'm going to compact. The way that I want to do this is I actually really want to step through this piece by piece by considering my order of operations. The order of operations is going to help you step through this. If I plug an x value into the function sine, the first thing that I do is take the sine value. When I do that, I get the black values in the sine wave. Then I would multiply by 1/2. Lastly, I'm going to subtract 3. So what I'm going to do is I'm going to actually sketch out those kind of interim graphs, so to speak, to imagine, okay, well, what does it look like after the first application of a transformation before I even get to that -3? And it's going to help me visually get to that end result much easier. So let's start with 1/2 sine of x. Again, 0 times 1/2 doesn't do anything, so that stays there. But 1 times 1/2, here we go. You can see my amplitude has decreased. I get a graph that's squished effectively rather than stretched. It's stretched by a value smaller than 1, so that I am half the distance to the x-axis that I originally was. Then, lastly, I'm going to now apply the -3. I'm now going to take each value and I'm going to shift it down. I do run out of space a little bit still. Oh my goodness. Let's make this a -2 just so I can fit it on there. Sorry, guys. Let's do that. Let's make this a -2. My apologies for being inconsistent here, but I want to make sure I can fit it on here a little bit better. So I'm going to go down -2 and move that down -2. The blue one, now notice I'm going to go down 1/2 and then 1.5. I'm also moving down that solid, consistent value of 2. And I give myself just enough room there. And there we go. And now I can fill in the actual function, and voila, we have y equals 1/2 of sine x minus 2. Let's do one more example. This time I want to go ahead and I want to multiply by a negative. So let's consider y equals negative sine of x plus 1. Same thing is going to happen. I firstly want to consider the negative sine of x, and then I'm going to shift that upward by 1. Okay, so let's start with the -1. And of course, as always, 0 stays put. Negative is going to flip this upside down and reflect it. And one thing you might want to consider using when you guys graph out these graphs on your own for me is to use dotted lines instead of a solid line like I did on the last slide. It can really help you keep the visual from not being too busy, where it's hard to follow step by step, especially as we start to complicate these functions a little bit more. Okay, I've got my y equals negative sine of x graphed. Now I'm going to go ahead and I'm going to add 1. So I'm going to shift all of these values up 1. And the last thing left to do is just to fill out my final function. Oops, that was a little sloppy. And voila, there we go. Lastly, we want to consider how can you figure out an equation from a graph. So here I have a graph that I've already got on here. Let's explore this a little bit and see if we can figure out what the equation is. So it looks like obviously it's been shifted upward because it's not centered around the x-axis anymore. I see a maximum of 6 and a minimum of -2. One good thing about all of these periodic functions is that they're all symmetrical. So we know that the midline is going to be smack in between, and I can go ahead and average 6 and -2, and I get 2. And so sure enough, if I graph right there, I can see that I have equal distances both above and below that midline. And that's going to actually tell me what my amplitude is, because now from 2 to 6, that tells me that my amplitude, or also my a value for the function, is 4. I can see that I'm starting at the midline, rising to a maximum, coming back to midline, falling to a minimum, and coming back to midline. So that is my sine wave. So I have a sine graph that has been multiplied by 4, and then lastly shifted upward to that midline up to y equals 4 sine x plus 2. Let's take a look at one more. Here we have another graph where now I can see I'm going from a maximum of -1 down to -5. So again, -5 plus -1, the average of those values is going to tell me that I have a midline at -3. This is telling me my K value. So there's my midline right there. K equals -3. My amplitude from that midline to a maximum, I can see that that's 2 units. So my amplitude is 2, but be careful, this is not to sine x minus 3 because I'm not starting at my midline. Here, I'm starting at a negative value, coming to midline, maximum, back to midline, and back down to minimum. If you recognize this as firstly not starting at midline, so therefore it's a cosine, but also it's upside down, that's telling you that this is actually -2 cosine of x minus 3. And there we can figure out the function. As always, head on over to Desmos and double check what you've come up with and make sure that the values match. One thing that you're going to be running into in Desmos, as well as if you continue to work in engineering, is that things aren't always scaled so nicely in radians. Sometimes things are scaled in normal numbers that we're used to instead of in terms of pi. This is actually the exact same graph as the previous one, but notice that that maximum value right here isn't labeled so nicely as pi. But that is exactly what that is. And you can see this is 3.14. It's just shifted a little bit to the right. The nice thing about the work that you're going to be doing in Delta Math is that it lets you keep adjusting and you can keep hitting the try button. And every time you hit try, it's going to adjust and you can wait until you've got just the perfect fit. So look for those values of pi. Think about 3.14. Think about 6.28 where there might be a 2 pi. But also think about half of pi. Think about 1.57 as well. Think about pi over 2, right? Okay, so with that, you guys, I'm done. Have a good day and go do your Delta Math. Thank you.